Here is something that should not work. Drop a rock in water, and it sinks. Drop a wooden block and it floats. Now drop a piece of the same substance, just in a different form, and watch what happens. Ice floats on liquid water. And that is genuinely, deeply weird. Most substances sink in their own liquid form. Liquid iron sinks through solid iron. Liquid wax sinks through solid wax. So why does ice break all the rules? And why, if it did not, would almost every lake, river, and ocean on Earth be a frozen graveyard? Let us start with the molecule itself. Water is two hydrogen atoms bonded to one oxygen atom, written H2O. You already knew that. But here is the part that changes everything. The oxygen atom pulls the shared electrons toward itself, leaving the hydrogen ends of the molecule with a slight positive charge, and the oxygen end with a slight negative charge. Scientists call this a polar molecule. Because opposite charges attract, each water molecule reaches toward its neighbors. These attractions are called hydrogen bonds, and they are the secret behind almost everything interesting water does. Now, in liquid water, those hydrogen bonds are constantly forming and breaking. The molecules jostle around, slide past each other, stay close but disorganized. Pack them tighter by cooling the water, and something strange begins. At exactly 4 degrees Celsius, liquid water is at its most dense. Squeeze more molecules into less space than at any other temperature. But keep cooling below 4 degrees, and instead of getting even denser, the molecules start locking into a rigid crystal lattice. Each water molecule bonds to exactly 4 neighbors in a hexagonal ring structure. Those rings are beautiful, and they are spacious. The locked lattice of ice actually holds the molecules farther apart than they sat in liquid water. Ice at 0 degrees Celsius is about 9% less dense than liquid water at the same temperature. 9%. That gap is why your ice cubes float in your glass, and why icebergs show only about 1/10 of their volume above the surface of the ocean. The physicist and Nobel laureate Percy Bridgman spent decades studying water under extreme pressure at Harvard in the early 20th century, eventually mapping out 17 distinct solid phases of ice. 17. Regular ice, the kind in your freezer, is called ice IH, meaning hexagonal. It is the only form of ice less dense than liquid water. Every other high-pressure ice phase sinks. Earth happens to keep water at pressures where ice is what you get. And that accident of pressure and temperature is enormous. Here's why enormous is not an overstatement. Think about a lake in winter. Air temperatures drop below freezing. The surface water cools, becomes denser, sinks, and warmer water rises to replace it. This convection keeps mixing the lake until the whole body of water reaches 4 degrees Celsius. Then, cooling below 4 degrees, the surface water actually becomes less dense than the water below it. It stops sinking. It stays on top. It freezes. And the ice that forms is, as we just established, lighter than the liquid water beneath it, so it floats and forms an insulating lid across the entire surface. That lid is everything. Ice conducts heat about 4 times less efficiently than liquid water. It traps warmth in the water below. Fish, bacteria, invertebrates, plants, the whole community of life under the ice, survives the winter in liquid water that stays right around 4 degrees Celsius, cold but not frozen solid. Limnologist John Magnuson, at the University of Wisconsin, led a landmark 1990 study published in Science that analyzed freeze and thaw records on lakes and rivers across the Northern Hemisphere going back to 1846. He found that ice cover on those water bodies had declined by 12 days over 150 years, a direct fingerprint of climate warming on the planet's water systems. Now, flip the scenario. Imagine if ice were denser than liquid water, the way almost every other solid is. Ice would sink the moment it formed. Cold winters would freeze lakes from the bottom up. no insulating lid. Every winter, deeper and deeper freezing, possibly all the way through. Spring might not be enough to thaw a lake that froze solid to the bottom in winter. Most freshwater life as we know it could not survive. The oceans might tell a similar story. One quirk of molecular geometry, one slight spacing difference in a crystal lattice, and life on Earth looks completely different, or possibly does not look like much at all. The chemist Linus Pauling, who won 2 Nobel Prizes, described the hydrogen bond in his 1939 book The Nature of the Chemical Bond as one of the most important forces in biochemistry. He was right, and this is one of the reasons why. The hydrogen bond shapes the water molecule into a polar traveler that builds open lattices when it freezes, makes ice lighter than its liquid self, and puts a blanket over frozen lakes every winter so the living world underneath can keep living. So the next time you drop an ice cube into a glass and watch it bob at the surface, you are watching the result of electron pulling, hexagonal crystal geometry, and a property so rare in nature that it might be one of the reasons anything alive exists to notice it at all. Pretty good for a cube of frozen tap water.